Recent observations of the interstellar object known as 3I/Atlas have added a new layer of intrigue to an already extraordinary visitor, as astronomers report the development of a faint bluish hue in the comet's coma following a rapid and unexpected brightening event. This subtle but notable color shift marks the third time since the object discovery that scientists have detected a possible change in its coloration, suggesting that the comet is undergoing complex physical and chemical processes as it travels through the inner regions of our solar system. Although none of the previous color changes appeared to persist for long, each episode has provided valuable clues about the composition, structure, and behavior of this rare interstellar wanderer. 3I/Atlas is only the third confirmed interstellar object ever observed passing through our solar system, making it an exceptionally important target for scientific study. Detected in early July, the comet was observed moving toward the Sun at a staggering speed exceeding 130,000 miles per hour, a velocity that immediately distinguished it from typical solar system comets. Such extreme speed is consistent with an origin beyond our planetary neighborhood, indicating that the object is not gravitationally bound to the Sun and is merely passing through on a hyperbolic trajectory. Based on its motion and other characteristics, astronomers believe that 3I/Atlas was ejected from its original star system billions of years ago, possibly more than 7 billion years in the past, before embarking on an unimaginably long journey through interstellar space. The age of 3I/Atlas is one of its most compelling aspects. If current estimates are correct, it may be the oldest comet ever observed, having formed during an early epoch of the Milky Way's history. Over billions of years, it would have drifted through the cold, dark environment between stars, largely undisturbed, preserving material from a distant and ancient planetary system. This makes the comet a natural time capsule, carrying chemical signatures that could offer insights into how planetary systems form and evolve beyond our own. Every change in brightness or color observed as it interacts with sunlight is therefore of immense interest, as it may reveal the nature of materials that have remained locked within the comet since the dawn of its home system. After its discovery, the comet's journey through the inner solar system unfolded in stages that alternated between accessibility and concealment. In early October, 3I/Atlas made a relatively close approach to Mars, an event that allowed astronomers to refine its trajectory and gather additional data. Shortly thereafter, however, the comet moved to the far side of the Sun relative to Earth, placing it in a position where direct observation with ground-based telescopes became extremely difficult. For several weeks, the Sun's glare effectively hid the comet from view, creating a gap in observations at a critical point in its passage. Only a limited number of space-based instruments, positioned at vantage points unaffected by Earth's line of sight, were able to continue monitoring it. During this period of partial invisibility, the comet reached perihelion, its closest point to the Sun, on October 29th. At that time, it approached to within about 130 million miles of the solar surface, a distance roughly 1.4 times greater than Earth's average distance from the Sun. While this is not an especially close perihelion by cometary standards, it was close enough to significantly increase solar heating of the comet's nucleus. Ordinarily, such heating causes volatile materials to sublimate, driving jets of gas and dust that form the characteristic coma and tail. However, what made this event remarkable was the scale of the brightening that appeared to occur while the comet was largely hidden from Earth's view. A day before perihelion, researchers analyzing spacecraft data reported that 3I/Atlas had brightened by several orders of magnitude, a dramatic increase that could not be fully explained by its distance from the Sun alone. This unexpected surge in brightness suggested that some additional process was at work, such as the sudden exposure of fresh volatile material or a structural change in the comet's nucleus. Alongside this brightening, the researchers noted that the comet appeared to be distinctly bluer than the Sun, a surprising observation given that earlier data had shown no such coloration. This bluish tint, though faint and not yet independently confirmed, immediately sparked discussion within the scientific community. The potential blue coloration is particularly intriguing because it may indicate the presence of specific gases being released from the comet. In comets, blue hues are often associated with molecules such as carbon monoxide or ionized carbon, which fluoresce under solar radiation. Ammonia and other nitrogen-bearing compounds can also contribute to bluish emissions under certain conditions. If such gases are indeed responsible for the observed color shift, it would imply that 3I/Atlas contains a rich inventory of volatile substances that are only now being released as the comet warms. This, in turn, could suggest that the comet's surface layers were previously insulating deeper materials, which became exposed due to cracking, fragmentation, or rapid thermal stress near perihelion. What makes this development even more compelling is the contrast between the current observations and the comet's earlier appearance. When 3I/Atlas was first observed in July, it displayed a distinctly reddish hue. Astronomers interpreted this coloration as evidence of a dust-rich coma, with fine particles scattering sunlight in a way that favored longer, redder wavelengths. Such dust-dominated activity is common in comets that are releasing large amounts of solid material, and it suggested that, at least initially, dust was the primary driver of the comet's visible appearance. Then, in September, observers reported a brief shift toward a greenish color. Green comas are often linked to the presence of molecules such as dicarbon or cyanide, which emit green light when excited by ultraviolet radiation from the sun. This intermediate phase hinted at a change in the balance of materials being released, possibly as the comet's increasing proximity to the sun activated different layers within its nucleus. However, this green coloration did not persist, fading as the comet continued along its path. The apparent pattern of transient color changes raises important questions about the internal structure and composition of 3I/Atlas. One possibility is that the comet is highly heterogeneous, with different regions containing varying concentrations of dust and volatile compounds. As solar heating penetrates the nucleus unevenly, different materials may be released at different times, producing temporary shifts in color. Another possibility is that the comet is undergoing episodic outbursts, in which pressure builds up beneath the surface until it is suddenly released, ejecting gas and dust in short-lived events. Each outburst could temporarily alter the composition of the coma, leading to the observed changes. Despite the excitement surrounding the reported blue hue, scientists remain cautious. The study describing the color change has not yet been peer-reviewed, and no independent observations have confirmed the findings so far. Observational challenges, including the comet's faintness and its recent proximity to the sun, make precise color measurements difficult. Atmospheric effects, instrumental sensitivities, and data processing techniques can all influence perceived color, especially for distant and rapidly changing objects. As a result, astronomers emphasize the need for continued monitoring now that the comet is becoming more accessible to Earth-based telescopes. As 3I/Atlas gradually emerges from behind the sun and moves farther into view, researchers will have more opportunities to test whether the bluish coloration persists or fades like the previous red and green phases. If the blue hue remains stable, it would strengthen the case for a genuine compositional change and provide a rare glimpse into the volatile chemistry of an interstellar comet. If it disappears, it would still offer valuable information by reinforcing the idea that the comet's activity is highly variable and sensitive to changing environmental conditions. Ultimately, the story of 3I/Atlas is still unfolding. Each new observation adds a piece to the puzzle, revealing a dynamic object shaped by billions of years of isolation and a brief but intense encounter with our sun. Whether the current color change proves to be temporary or enduring, it underscores how much there is still to learn from these rare visitors. As technology improves and detection methods become more sensitive, future interstellar comets may be discovered earlier and studied in greater detail, building on the lessons learned from 3I/Atlas. For now, astronomers continue to watch closely, aware that even subtle changes in color or brightness may carry profound implications for our understanding of the wider galaxy and the ancient materials that drift between its stars.